Hello there and welcome to a brand new lesson. This is How Beyond Numbers, where we learn maths the easy way. In this lesson, we are looking at the domain, range, and zeros of a function. By the end of this lesson, you should be able to identify and state the natural domain of a function by recognizing its restrictions. You should be able to find the range of a function by analyzing what inputs are possible. You should be able to understand and apply the two main domain restrictions, that is the zero denominator and the negative square root. You should be able to find the zeros of a function by solving the function being equated to zero. And finally, you should be able to interpret zeros graphically as x-intercepts of the function's graph. These are some terms or vocabularies we'll be using as we go through this lesson. I advise you pause at this moment and quickly take a glance. Without much ado, take your notebooks, your pens, so we learn together. It is always advisable you learn by actually practicing what I teach as well. So let's start by looking at what the natural domain is. When we talk of the natural domain, it is simply the largest set of all real x values for which the function is defined. The most important thing here is what? Defined. When we say a function is defined by x values, it simply means that if you put the x values in the function, it gives you a result, a proper result. Now, unless otherwise stated, the domain of every function is all real numbers. You see, and we actually write it as this r over here, all real numbers. But there are two main situations that force restrictions, and that is what we want to consider. The first is the zero denominator, and the second is what? Negative under a root. Talking of the zero denominator, you know that if you have a fraction, so let's say a fraction written as a over b, if b is equal to 0, the fraction we say is undefined. You see, so division by 0 is undefined. Hence, if you want to list the domain of a function, you exclude the values of x that makes the denominator equal to 0. That is the first restriction when it comes to the natural domain of every function. As I said earlier on, when no restrictions are given, then we can directly say the domain is all real numbers. But when there are these restrictions, the first one being the zero denominator, then we say we exclude those values of x for which the denominator becomes 0. So for instance, if we have an f of x, which is equal to a 5 over, let's say, an x minus 2. If you have to evaluate this, and then say we actually want a f of 2, what is going to happen? So we are going to get a 5 over x, which in this case is 2. So 2 minus 2. And we know what 2 minus 2 gives us. We have 5 over 0. This is what? Undefined. And we don't want that to happen. So if we actually want the domain of this function, we can say the values of x are all elements of R, but then x should not be equal to 2. You see, we'll be solving more of this, but then this is just to explain what the concept means. The next restriction we want to look at is the negative under the radical sign. Now, in the domain of numbers, the square root of a negative number is not real. For instance, if we have square root of negative 1, then we know what it becomes. It becomes an I, which is an imaginary number. And we don't want to work with imaginary numbers. We want real numbers. So anytime we want to list out the domain of a function, especially if it is under the radical sign, then we'd have to limit ourselves to only the values that makes whatever expression you have in the radical sign to be equal to or greater than 0. Because if it becomes less than 0, then you are entering into an imaginary number domain, which we don't want that to happen. So if we have a function such as f of x, and f of x is simply the square root of, let's say, an x minus 4, then if you want to list out this domain, we would have to make sure our x minus 4 is always a greater than or equal to 0. You see, and making x-intercept that we have our x being greater than or equal to a 4. So this simply means if we are to solve for x, f of x, where x is equal to 4, then we are going to get the square root of 4 minus 4, which is equal to what? The square root of 0, which is actually 0. But if we were to take any number that doesn't obey this principle here, such as 3, we are going to get a 3 minus 4, which will give us a negative answer. And the negative square root is not in our real domain. So that will be it for now under our domain. We'll look at range and also look at zeros, after which we now solve questions on them. But a very quick strategy: anytime you want the domain, all we want you to do is to look for fractions. You see, that is with respect to the first restriction, that is the 0 denominator. So you look for fractions. If there are fractions, then quickly set the denominator to be what? Not equal to 0. And then you'd solve for what? Your values. But then if there are square roots, then all you need to do is to set the expression under the radical sign to be greater than or equal to 0. But then if you don't have a fraction nor a square root, then it simply means the domain is simply all real numbers. Every real number will make our function defined. That is it for what? The domain of a function. So with all that we have done theoretically, let's actually look at these graphs of the various functions, so we see what we are talking about. We get to know what the domain is. So we are saying the domain is the set of all possible values of the x. You see, so this is a linear graph, and you realize that for all values of x that I pick over here, it gives me a corresponding value. So as I move along this graph, you see I have pairs of what? Values. That is the x and then its corresponding y. Now, even if I'm to zoom this out, you realize that the graph still continues because it is defined everywhere on our graph. On the other hand, let's look at this rational function here. This one is actually 1 over x minus 1. 1 over x minus 1. You realize that if I put x to be 1, we are going to get what? 1 minus 1 should give us 0. So if the graph is being drawn, you realize that it doesn't get to x equals 1 because it is undefined over there. So if I'm even to test for the value x equals 1 and I'm putting it in a function, it says what? The function is undefined here because it is not part of the domain. You see, so this is how that graph is. And we say it is not continuous at x equals 1. It is very easy to get it with the graph, but we actually going forward wants to solve it and then prove that really when we substitute x equals 1, it is not going to work. So this here is also another rational function where the denominator is what? X minus 3. So you realize that this line, which is x equals 3 over here, our graph does not touch it. No matter how up it goes, it will never touch. Because immediately x becomes 3, as we would see over here, it is going to make the function undefined. Let's look at the last one that will involve a square root. So this function you see here is a function of the square root of x. Now, if I'm to zoom out, Do you see what happens? So for the x values we have, we can find the square root of positive values. And as you can see, 4 here gives me what? 2. So if you are to zoom out, it goes on and on and on. But the graph does not even appear on the negative side of our Cartesian plane. You see, so if I'm to put x to be, let's take any negative number, so -4, it gives me undefined. You see, so this is what we actually want to solve for. Now that we have a fair idea of what the domain is, let's look at what the range also is. So unlike the domain, the range is what we see over here. It is the complete set of output values that are actually produced by all inputs in the domain. So if we put our value of x inside the function, the answers we'll get, or the set of answers we'll get, is what we call the range. We can find the range of linear functions, of quadratic functions, of square root functions, and also of rational functions. We would go to the graph and then have a feel of what it actually looks like visually. So for linear functions, the range is all real numbers. Every real number forms part of the range of what? Linear functions. On the other hand, for quadratic functions, the range starts at the minimum or maximum. I'll show you that as well, the minimum or maximum. For square root functions, the range is always for y which is greater than or equal to 0. Because you know, for a square root, we definitely do not have the square root of a negative number. So the range will represent all numbers greater than or equal to 0. Then for rational functions, on the other hand, what you have to do is the range is only, so you can say it is the set of all real numbers, all right, except that value for which what the y values is equal to 0. That one involves a little bit of calculations, and we would see that when we begin solving. Now let's go to the graph and actually understand this visually. So let's start with linear functions. Now we said the range is actually the set of values on the y. You see, so with this graph we have over here, if I'm to zoom out, you realize that if we look at the y-axis, it corresponds to what? Every value of x that we put. You see, so for all the points I have here, let's look at this particular section of our screen. You realize that any point where I put my x values, it has a corresponding y value. So even including the one you can visibly see on our screen. So look at this point, and then let's look at this section once again. So this side, or this side, even when x is 51, it still gives us a value of y. If we are to zoom out and we still proceed, you see, even when x is 616, it still gives us a value of y. And it also applies even on the negative domain as well. So on the negative domain here, as you can see the value of x over here, you realize that what? It still gives me a value of what? Y. That is for the linear what? Graph. On the other hand, when it comes to a quadratic function, there is a different story altogether we have over here. We said for quadratic functions, the range starts at the minimum or the maximum value. So for this function over here, which is 1x squared minus 1, that is the function that has been graphed over here, the value of y would only start here. This is a minimum function. So the value of x will start here and then it goes upward. So if I'm to zoom in, we can take a value of y over here. In this case, the smallest value of y you can ever get is what? The -1. So with the -1, it then goes on and on and on upwards. You see, but then let's talk of one that will actually go downwards. So for this function you see over here, that is a negative 1x squared minus 1. I can change it and then bring it up a little. So for this one here, it has a maximum value of y. Any other value of y that goes upwards is not defined. So for instance, if I'm to test for y being what, 10, as I'm doing over here, if I check, it says that is not in the range, because there's no value of x that will give us that. You see, so it is not part of the what, the range. So that is it for quadratic functions. Then we come to square root functions. So for square root functions, let's take something like this. Now, square root function says that the range is always y being greater than or equal to 0. So if we look at what we have over here, this is where, our x-axis is also called the line y equals 0. And you realize that the graph does not even come down to where you have the negative values of y. You see, irrespective of how the graph might look like, it still starts at what? 0, right where y is 0. So if I'm to shift forward or backwards, it doesn't occur. Unlike the linear where you see it goes down even to the negative domain of our y values. For square root, it only starts at the positive domain, irrespective of how your function looks like. You see, so as I change it, it still remains the same, always starting at y equals 0. Then we have rational functions. So for a rational function, its graph is a little bit interesting. It says you have to identify the value for which y can never be produced. So if you look at this function, for instance, it's a rational function of 1 over x plus 2. If we start all the way from the x-axis, let's start from the bigger number. So it comes all the way, we have 6, 5, 4, 3, 2, and as we move closer to this value here being x equals what? Negative 2, because if we put negative 2 here, we have negative 2 plus 2 gives us 0. And we can't have a 1 over 0. So as I proceed here, you see it keeps going up, but it will never touch this line we have here. That is the x equals negative 2. On the other hand, even if we are to start from the negative domain, we move all the way, moving to the positive, and it will also never get to x equals negative 2. Because immediately as it gets there, we are going to have an undefined function. You see, so if I'm to zoom in, you realize that our line will never touch this x equals negative 2. So this is the visualization of the range of a function. Now the last thing we want to look at is the zeros of a function. So when we talk of the zeros of a function, it is simply what the x values for which the function equates to what? 0. So what value of x do I put in my function so that I'll get 0? On the graph, these are the x-intercepts. That is where the curve crosses the x-axis. It is very, very easy to solve. So all you need to do is to what? Equate your function to 0 and solve. If it is a linear, you use your linear method. If it's a quadratic, you can use your almighty formula, the quadratic formula, the completing of squares, and then you'd go. If it is a polynomial, you can use any of the polynomial methods as well. That is, you can use the remainder theorem and what have you, or factorization to equate to 0. Simply put, the zeros of a function is what? The set of values of x for which our function equates to 0. And it is simply the x-intercepts. So on our graph here, let's look at an example just to enhance our understanding. This is a linear function, you see. So with it being a linear function, 2x plus 2. At what value do we get all of this being equal to 0? And we said it is simply the x-intercept, you see. So that is this point over here. And with my functions here, I can test what value of y becomes 0. So if I put 0 here, it will tell me that it is achieved at x equals -1. This is the x equals -1. We have 0, -1, 2. And at x being equal to -1, my function will yield a 0. You see, so on a graph, the most important thing is coming to identify this point over here. You are good to go. For quadratic, on the other hand, we know quadratic have a degree of 2. So if it has a degree of 2, then it simply means there are always two values that achieves this state. So if we are to use this graph I have over here, you see it has 2 points. You see it has 2 points. So if we are to test over here where our function equals 0, it gives us 2 points. That is -1.732 or a 1.732. Those are these points we see over here. So if I'm to zoom, you can even see that clearly, this coordinate and also this coordinate as well. Then when we come to square root, we know it never goes to the negative domain. It always starts at what? Here. That is where y is equal to or greater than 0. So for such, it is always the point of, or the point at which your graph starts. You get it? Because for the square root, we said earlier on that the range of value is always greater than or equal to 0. So as we solve some questions, you would get to understand and appreciate it more. For rational, on the other hand, you see, it depends on how the rational function looks like. For this, you'd obviously not get a 0 because it doesn't touch the x-axis. But let's change this and then we see. So unlike the previous one, this rational function actually touches our what? X-axis. Now this is the graph of x plus 1 all over x. That is what we have over here. So on the graph, all we need to do is to identify where it intercepts our x-axis. And to even test for it using my functions here, if I put a 0, it is going to give me what? A -1.0008, approximately a -1. So you realize that if I put -1 here, it yields a what? A 0 in my function. So that will be all for the visualization. Now let's actually solve some questions to enhance our understanding. So as we always do, we'll be solving 5 questions in this session in increasing order of complexity. I advise that you'd always pause before I begin the questions, solve on your own, and then you unpause to check my suggested solution. I'll try as much as possible to get the graphs of all of these functions so that we don't just solve theoretically, but then we can also look at what it means on the graph as well. So that much I do, let's quickly solve our questions. It says, state the domain of each function. So we have all these functions here and we want to state their domain. For the first one, which is f of x equals x squared plus 3, we want the domain. Now there are restrictions if only it is a fraction or a square root. But in this case, we don't have a fraction nor a square root. You see, in that case, we just say the domain is what? The set of real numbers. That simply means that the x values can be any value at all on our number line, and it will still make this function valid. So since there's nothing to solve, we can say the domain x is an element of what? All real numbers. As simple as that. The second one, on the other hand, that is b, it says j of x is equal to 1 over x plus 5. Now this is where we can actually solve something. We know for a fraction, denominator can never be what? 0. So the domain of this function should be such that anytime we evaluate the denominator, which is x plus 5, it should not be equal to 0. We will now have to make x the subject. So making x the subject, we have our x, which is equal to what? A negative 5. So it simply means that our domain, this is how we conclude. We then say our domain is what? X is an element of real numbers, all right, but then x can never be equal to what? Negative 5. You see, so x should never be equal to negative 5, because if you put x to be negative 5, this whole thing becomes 1 over negative 5 plus 5, which is 1 over 0. That doesn't exist. Do you see? So our last question, that is c. It says h of x is equal to the square root of 2x minus 6. Now we know for square root it is undefined if the expression inside the radical is actually less than 0. You see, so the domain of this would be any set of values that would actually make what we have here, that is the 2x minus 6, to be greater than or equal to 0. If it is able to satisfy that, then it will form part of the domain. So we would have to make x the subject. We have 2x is greater than or equal to what? 6, because this negative 6 moves to the other side to give us what? A positive 6. Dividing both sides by 2, we have our x, which is greater than or equal to what? A 3. So with this, we can also say that our domain is what? X is an element of R. That is all values of R. But then the x should be greater than or equal to 3. You see? So all values of R, but then it has limitations. It should be greater than or equal to 3. In which case, if it is 3, we can get 2 times 3, which is 6, then minus 6, giving us 0. Square root of 0 is 0. Then afterwards, any other value that is greater than 3 gives us a positive number. Apart from writing it this way, we can also use the interval notation. So we know it starts from 3 all the way to infinity. So you put a square bracket here to indicate that 3 forms part of it. You see, now since infinity has no limit, we just bring this over here. This is another way you can write your domain, that is from this one here. As we've been able to solve this, let's look at their graphical representation so that we can appreciate what is going on here. Now, this is the first one we have over here. That is the x squared plus 3. And we said its domain is all values of R. And that is true. You see the graph we have over here, if I'm to zoom out, you see it goes all the way up. Now, there is no value of x that if you put in here, it won't give you an answer. Even though 100 is not within our range of view, if I'm to put 100 for x right here, it is going to give me an answer for what? Y. That is a 10,003. You see, so every value of x would actually make it possible for us to get a y. Hence, we say it is defined on R. Now, let's look at the second one. So, for the second one, that is 1 over x plus 5. When we solved, what did we say? We said the x value cannot be 5. So, you realize that this around this point is where we have x. We said x value can never be negative 5, you see. So around this point is where we have our x to be negative 5. And if you are approaching x from the right hand side, it never reaches this point, because this point that is undefined. So even if we are to zoom out, you realize that the line will continuously move up, but then it will never touch the line x equals negative 5, you see. And if we are to test over here as well, if I put x to be negative 5, you see that it gives me undefined. So the function is undefined here. Hence, there is no line that will touch that over here, you see. Then the third one as well. So for the third one, we said the value of x would never be less than 3, or it is from 3 and above. As you can see the graph, you see from 2, 3, 4, so it starts from what? 3. And the graph never appears within this range. It is from 3 and above. That is where the domain of x would actually work. So with all this done, let's look at our next set of questions. For these, we have to find the zeros of. So you have f of x being 3x minus 12, and then g of x being an x squared minus x minus 6. We want the zeros of these. For the very first one, it says f of x is equal to a 3x minus 12. And we know what the zeros mean. So for the zeros, the function should be equal to 0. So if that is the case, then it simply means our f of x, which is what? The 3x minus 12 should then be equated towards 0. So solving for our x, we have 3x is equal to negative 12 moves to the other side to give us a 12. Dividing both sides by 3, we have x being equal to a 4. You see. Then we come to the second one. So for b, it also says g of x is equal to x squared minus x minus 6. So we say for the zeros, then it simply implies that our g of x should be equal to 0. This is the g of x. So it simply also implies that the x squared minus x minus 6 is then equal to 0. We solve this using our method of what? Factorization. So if you factorize x squared minus x minus 6, you'd be getting an x minus 3 and then an x plus 2. I want to assume you know how to solve these factorization questions so that we wouldn't spend more time on it. So equating the brackets to 0, we have x, then minus 3, which is equal to 0. Making x the subject, we have x equals 3. Then for the second one, we also have x plus 2, which is equal to 0. Making x the subject, we have an x which is equal to a negative 2. You see? So we would say x is equal to 3, or x is equal to what? Negative 2. Those would be the zeros of this function, which means we have to substitute x to be any of these, we are going to get 0. Hence our conclusion. We then say that therefore for the first one, the 0 is at what? X equals 4. And then for the second one, the 0 is at x equals 3 and x equals negative 2. If we are to visualize what we have just done for the first equation, which was 3x minus 4, look at what is happening carefully. So you see that at x equals 4, then our y value will be equal to 0. You see, we also said that the 0 of the function is simply the x-intercept. So that is what we have actually done here for the first one. Then for the second one is actually a quadratic. So for quadratic, this is how their functions look like. It's either a u or what? An n. This one is a u. So if we zoom, we want to take note of these values. So this value, this particular value here, then this particular value over here. Remember, we said if x is either 3 or negative 2, then our function is 0. So looking here, this is x equals 3 and this is x equals negative 2. You see, so it means our solutions were what? True and then valid. So let's look at our third question. It says you have to state the domain, the range, and then the zeros of this function. The function is what? F of x equals x squared minus 4. So you have f of x being equal to x squared minus 4. Let's start with the domain. So for the domain, you realize that there is no fraction nor a square root. We said if there's no fraction or a square root, then it simply means the domain is every element on R. You see, so our domain, we would simply say there is no restriction and that x is an element of R. That is all our domain. Then we come to our range. Remember, we said for range, for linear functions, we said the range is also all element of R. For quadratic functions, we said the range actually starts from the minimum or maximum value. You get it? And then we also said that for square root functions, the range is what? Y being greater than or equal to 0. And we have that of rational functions as well. In this case, we are talking of a quadratic function. So for it to be quadratic, then the range is actually starting from the minimum or maximum value. In our subsequent lessons, we'll look at quadratic functions and really understand what the minimum or the maximum value is. But for now, let's try answering this question. Now we know that whatever value of x that we'll put here, it will definitely be greater than or equal to 0. So to solve for the range, there is a nice procedure we use. So you see, for the range, what do you do with, you let your function f of x be equal to what? Y. And we know what f of x is. F of x is simply x squared minus 4. So if this is f of x, then we are saying it is equal to what? Y. After which you look for x. That is, you make x the subject. So making x the subject, we have x squared being equal to a y, then plus 4. X is what we are making the subject and not x squared. So we find the square root of both sides. If we find the square root of x squared, we have an x, which is equal to the square root of y plus 4. With this, you would now find the value of y that makes this not to exist. You see, so for a radical sign, we know it doesn't exist what you have in the radical is actually what? Less than 0. So for this to exist, we would have y plus 4 being greater than or equal to 0. Then making y the subject, we have y, which is what? Greater than or equal to 4. This here is the range of values of y. You see? So we can then say that for the range, so for range, our f of x has values that are greater than or equal to what? 4. That is the range. Then we now come for the zeros. We know for zeros, then it simply means f of x is equal to 0. You see? So we come and then say for zeros, then it simply implies that our function f of x is equal to what? 0. And that is to say x squared minus 4 is equal to 0. Then we make our x the subject. So you have x being equal to what? X squared being equal to 4. We find the square root of both sides. We have x being equal to a plus or minus 2. So the zeros are what? X equals 2 or x equals negative 2. And that is all. So with that, you've realized that we have gotten our domain to be what? All the elements in R. We have gotten our range to be f of x is greater than or equal to negative 4. And then the zeros are what? X equals plus or minus 2. For this fourth question we have, it says f of x equals x plus 1 all about x squared minus 9. And we have to find the domain. The domain this time around is not a linear one, such that we could easily say the domain is all elements of R. But then this time around we have f of x being equal to an x plus 1 all over x squared minus 9. So in this case, there are some values of x that will not make it possible for this to work. And especially that is the denominator. So we would have to set the denominator to 0. So you say for domain, our denominator must not be equal to 0. So we have x squared minus 9. It shouldn't be equal to what? 0. Then we make x the subject. So we have x squared being equal to a 9. If you find the square root of both sides, we have our x being equal to a plus or minus 3. You see, that is to say that if we have to find f of 3, we know it is going to be a 3 plus 1 all over a 3 squared minus 1. This would have given us 4, but it's 4 over 0, which is undefined. The same applies to what? Negative 3. So negative 3 also gives us what? 0, which is undefined. So we then conclude by saying that the domain is all values of R. All right. But then the x should not be equal to 3. Neither should it be equal to what? Negative 3. So these two values are excluded from our domain. To look at how this graph actually looks like, it's an interesting graph. So this is it over here, you see, and it has 2 points for which the lines of the graph doesn't continue. The first one is what? The 3, which we have over here. So you see it moves all the way from the bigger values of x and then goes up, but then it makes sure it doesn't touch the line x equals 3. The same applies over here. It never touches the -3. It goes up and goes up, but then never touches the -3. You see, if you have to zoom over here, you see what is happening. So that is it. See, it doesn't touch here. So this is how it looks like. Let's now solve our last question for this session. So our last question we have here says f of x is the square root of 25 minus x squared. So f of x equals square root of 25 then minus x squared. And what we want the domain. First of all, we want the domain, the range, and the zeros. Now, I would want to believe by now you are confident in solving these questions. So if you've not even paused any of the video to solve before looking at the suggested solutions, you can do so now. If you're able to do it, well done. Now let's solve together. It says you have to find the domain. So we know for the domain, we know that it will only be possible if the x values actually give us what? An answer that is greater than or equal to what? 0. So for our domain, 25 minus x squared should always be greater than or equal to 0. We then have to make x the subject. So making x the subject, we have our 25 being greater than or equal to what? X squared. You might ask, why did I choose to maintain the 25 here? It is actually the same thing if you solved it otherwise. That is to say, we have negative x squared greater than or equal to then negative 25. You see, then with that, you are going to divide both sides by -1. You know, when it comes to the radical sign with the inequalities, if we divide by negative, then the signs change. So dividing this by -1, we have x squared then less than or equal to 25. And that is the same thing we have gotten over here. That is x squared. Since we are reading from this, the lesser side is facing x squared. So less than or equal to 25. Now, making x the subject, we have x, which is less than or equal to, that is finding the square root of both sides. We have plus or minus 5. Now, this here is actually talking of range of values. So if you want to rewrite this, then it is a -5 is less than or equal to x is less than or equal to what? 5. So the only range of values for which x squared can be less than or equal to 25 is within this range. If you take anything out of this range, x squared is going to be greater than 25, which will affect our radical sign. For instance, if I'm to take a value that exceeds this range, so let's say around 6, if I take 6 squared gives me a 36. And 25 minus 36 is going to be a negative answer, which will make this radical undefined. If I take a smaller value from this range outside, such as let's say -6 as well is going to give us a 36. You see, and 25 minus 36 is going to also give us undefined. So it means the only range of values of this functions, that is the domain, excuse me to say, the only domain of x is within this set. If you want to use the interval notation, then we are going to use this. So we have -5, 5 to tell us that what the x ends at -5 within that interval, which also ends at 5. So this is our domain of this function. This one was an interesting one, of course, and we would even see it graphically. The second one says you should find the range. You should find the range. You remember how we were able to work for the range. So for range, we said that we should always let our y value be equal to the f of x. And if y value is equal to f of x, then it simply implies that our f of x, which was what? The square root of 25 minus x squared, is actually equal to what? Y. Then we need to make y the subject. If we square both sides, squaring all of this takes out our square root. So that we have 25 minus x squared being equal to what? The y squared. What do we want to make the subject? We want to make this x the subject. So we have 25 minus y squared is equal to x squared. We wanted to avoid the negative, so we took this negative x squared to the other side and we brought the y squared to the left hand side so that it becomes a negative over here. Then since it is x squared we want, since it is x we want, we then find the square root of both sides. So if you find the square root of both sides, we have 25 minus y squared, which is then equal to what? Our x. So this is our x value. So 25 minus y squared. Now this simply means that we want the set of values for which what we have under the set or the radical expression is what? Greater than or equal to 0. Because immediately as it becomes less than 0, this ceases to exist. So it means we need our 25 minus y squared to be greater than or equal to 0. Making our y the subject, we have what? 25 greater than or equal to y squared, which can then be read as what? Y squared is less than or equal to 25. Making our y the subject simply means we'll have to find the square root of both sides. So our y is less than or equal to plus or minus 5. Now this can then be interpreted as negative 5 less than or equal to y less than or equal to what? 5. But this is where we have to analyze what we are doing. Looking at the domain, the x values gives us what? X is a range of negative 5 and 5 inclusive. So this is to tell you that even if you have a negative value of x, you are still going to get a positive value of y, because at the end of the day we square it. You see, so for the x values you can take negative, all right, but after evaluating, y values are never going to give us what? A negative answer. You see, so we use that to make an informed decision here, and that gives us y being always greater than or equal to 0. So it simply means for this whole range we have over here, we have to truncate it based on this limitation we have here. And that is to say, the range of values of y is then going to be what? Just the interval between 0 and then 5 inclusive. Or written as y is an element of R, that is all element of R. But then the y should be less than or equal to 5 or greater than or equal to what? 0. Any of this works fine. This is our range. Then the last one says we want our what? Zeros. So for zeros, we know the conditions already. So we know that for zeros, f of x should be equal to 0. Now, if f of x should be equal to 0, then it simply implies that our function f of x, which is the square root of 25 minus x squared, should be equal to 0. And this can only be equal to 0 if we have 25 minus x squared being equal to 0. Making our x the subject, we have 25 being equal to an x squared. Finding the square root of both sides, we have plus or minus 5 being equal to our x. These are the values for which word x, or f of x, is equal to what? 0. So in total, what are we going to say? We say we have our domain being what? -5 to 5, the interval between -5 and 5 inclusive, and our range being the interval between 0 and then 5 inclusive, and then our zeros are what? Plus or minus 5. Let's look at how this looks like graphically. As you can see, this is the graph of 25 minus x squared. So as you can see the graph over here, first of all, talking of our range of values, the only set of values of x we had was what? Between -5 and then +5, and that was all. Then if you look at the range of values of y, it is from 0 to what? The +5. That was all for y. It didn't extend to the negative domain. Then our graph comes all the way toward this point. These are the zeros of our graph. We said the zeros are just the intercept of y. As simple as that. So we've come a very, very long way. This lesson has been very long, and I do hope it was worth it and you were able to understand all the concepts that I tried to explain. As usual, I'll leave you with some exercises so you try on your own. So here we have just 5 questions for you to try on your own to test your understanding. This is how Beyond Numbers, where we learn maths the easy way. If this is your first time on this channel and you think it would be useful to you, you can choose to subscribe if you so do wish, so that anytime I release a video, you'll be notified as well. See you in our next lesson, and bye for now. Do stay safe.